All right, in part 7 of the lecture, we are going to consider Taylor's remainder. So, what is Taylor's remainder? So, basically, if we have Taylor's polynomial of degree n, then we consider it as approximation to our function f. So, the difference between our function and this approximation is the remainder, right? Now, generally speaking, you can think of this difference between our function and approximation as just something like Rn of x. And of course, it is always true that f of x minus Tn of x equals some Rn of x. I mean, you just denote uh, this difference as Rn of x. But the question is, what can we do with this? And to do something about this remainder, so there are different theorems about particular forms of this remainder. So, and Taylor's formula is actually is an umbrella terms of several theorems that claim that the remainder of uh, the Taylor polynomial can be represented in a particular form. So in this case, this particular form is called Lagrange's remainder. Lag- Lagrange's remainder. It's not the only one, so there is also Peano's remainder, there is Cauchy's remainder, there is integral remainder. If you Google Taylor's formula, you will probably even find more. But uh, today we just need to, we are going to work with Lagrange's remainder. Now, well, Lagrange's form of Taylor remainder. Yeah. Now, what does it mean? So it means that there exists some number c between well, c is between a and x, right? So c belongs to either the interval from a to x, well, I guess it could be exactly or from x to a, depending on whether x is bigger than a or x is smaller than a, such that this equation holds. Okay. Now, why do we care about the particular form of the remainder is because of the following kind of expansion, right? So it means that our function can be expanded as its Taylor polynomial plus this remainder. And imagine that, n goes to infinity, right? So, and if n goes to infinity, and if it happens that this term goes to zero, it means that our function can be expressed as the sum of the infinite series, right? So basically, the important conclusion here is that if the limit of the remainder as n goes to infinity is 0 for every x, then f equals the sum of its own Taylor series. Okay? And now we're going to apply this theorem to derive Taylor series expansions for trigonometric and for exponential functions. Okay, so find the Maclaurin series of sine x and show that it converges to sine x at every x, right? So to find the Maclaurin series of sine x is not really that hard, because what we do is we begin with, so sine x is our original function or derivative of degree 0. Then when we differentiate it, we get cosine x. So its first derivative is cosine x. Its second derivative is minus sine x. Then its third derivative is minus cosine x. Then its fourth derivative is, we're back to square one, it's sine x again. Then its fifth derivative is going to be cosine x, and so on, right? So it's going to repeat. Um, so Maclaurin series means that the word Maclaurin series means that a is 0, right? So we are finding powers of x, right? So we need to show that it converges to sine x at every x. I mean, so finding the Maclaurin series is not that hard, but to prove that it converges to sine x is somewhat more challenging. So anyway, so when a is 0, so sine 0 is 0, cosine 0 is 1, then minus sine 0 is 0, minus cosine 0 is negative 1, and then it's going to repeat itself, right? Um, and so on. So the consecutive derivatives of sine x evaluated at 0 are just 0, 1, 0, minus 1, 0, 1, 0, minus 1, and so on, right? So, which means that to construct the Maclaurin series, what we do is the term of degree 0 is just 0. Then the term of degree 1 is going to be x. Then there is no term of degree 2. Then there is minus here, so minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on. So minus x, so they are alternating, and only odd powers are included. So minus 7 factorial plus x to the 9 over 9 factorial, and so on. Right, so this is the Maclaurin series for the sine x. Now, if you want to write it in compact form, you can notice that, well, given that only odd degrees are present, and an odd degree can be written as x to the power 2 and minus 1, 2n plus 1, doesn't matter, so 2n plus 1 over 2n plus 1 factorial and times minus 1 raised to the power, well, okay, so we are going to start from 0, I guess, so that x is present. X to the power 0 plus 1 is, yeah, correct, so we're going to start from 0, and it's probably going to be minus 1 raised to the power n, because it starts from 0 and it starts from a positive term, right? So this is our Maclaurin series for sine x, right? So and the question is to prove that it actually equals to sine x. Now to prove that its sum actually equals sine x, right? So we need to try the remainder, right? So the remainder is our sine x minus tn x, right? So and this is, so if my sine x is f, right? So the remainder is going to be f derivative of sine x of degree n plus 1, of order n plus 1, evaluated at some point c, and c is basically between 0 and x, yeah, between 0 and x, divided by n plus 1 factorial times x raised to the power n plus 1, right? So this is the remainder. Oh, okay. So, and the question is, we want to verify that it converges to 0, right? So as n goes to infinity, that it tends to 0, right? So now, but generally speaking, in order to verify that some sequence approaches 0, we can introduce the absolute value here in front of everything, and then prove that the resulting sequence approaches 0, right? Now, why do we want the absolute value is because of the following. So notice that this f n plus 1, so the derivative of n plus 1, of order n plus 1 at the point C, is in fact, so the derivative of every order of the sine is going to be either sine or cosine, right? So plus minus sine or cosine. So this is essentially plus minus sine or cosine evaluated at the point C. And of course, its absolute value, in any case, is going to be less than or equal to 1, right? So the remainder of the Maclaurin series, so the remainder of sine x minus tn x, the absolute value of the remainder is of course bigger than or equal than 0, because it's absolute value, and is less than or equal than what? Then absolute value of x raised to the power n plus 1. So now I'm just replacing this derivative term with just 1, because it's either sine or cosine or plus or minus sine or minus cosine, and in any case it's less than 1. Its absolute value is less than 1 divided by n plus 1 factorial. And now we can apply the squeeze theorem. So basically this goes to 0, this goes to 0, so which means that whatever is in between also goes to 0. Now I probably need to explain a little bit to further elaborate of why this goes to 0. So the intuition here is that the numerator is consecutive powers of x, and the denominator are factorials, right? So as n grows, and basically both numerator and denominator are just products of a lot of numbers, but in the numerator the numbers are all the same, so it's just absolute value of x is multiplied by itself many times, and in the denominator it's really the numbers that you are multiplying with are growing, and of course eventually they are going to get bigger than x, and then you will they will tend to 0. But if you're not convinced, so let me maybe do this limit again. So to prove that this limit is 0, I'm going to apply one more round of the squeeze theorem, right? So let me do it here. Now, x raised to the power n plus 1 divided by n plus 1 factorial is really x divided by 1 times x divided by 2, well, absolute value of x, times and so on, times x divided by n times x divided by n plus 1, right? Now, so x itself is probably going to be bigger than 1, right? So which means that this term is probably going to be bigger than 1. So the next term is probably going to be, again, bigger than 1. But at some point, x is going to be less than n. So when n is bigger than x, um, then absolute value of x divided by n is going to be smaller than 1, right? So now at which point is it going to happen? So exactly at the following point. So if x at some point here, I will get the floor function of absolute value of x, which is the largest integer not yet exceeding x, and this is still bigger than or equal to 1. The next term is going to be absolute value of x divided by absolute value of, well, floor function of absolute value of x plus 1, and this is strictly less than 1. Then it's going to be absolute value of x divided by the floor function of x plus 2, which is again less than 1, and so on up to the second last term is going to be absolute value of x divided by n times absolute value of x divided by n plus 1. All right, so this is still going to be less than 1, and the last term we're going to keep it as is. Okay, so here is what I'm going to do. I'm going to just denote this whole thing by, I don't know, some number m, whatever. Right? So all these terms are less than 1. So which means that the whole product is going to be less than m times absolute value of x divided by n plus 1. And here, if you take the limit as n goes to infinity, this is going to be 0. Because now we just have a constant divided by n, and it clearly goes to 0. Okay? So this is why, this is how we can see that the limit of some number x raised to the power n plus 1 divided by n plus 1 factorial, or for whatever reason, so x raised to the n divided by n factorial, or anything like that. So powers of some fixed number divided by factorials. So a limit of such a sort is 0. Okay, and that's basically it. So now we have proved that the limit of the remainder is 0, which essentially means that the Maclaurin series of sine x actually converges to sine x. So its sum equals sine x. Well, here is the same thing kind of written nicely with some pictures, right? So these are consecutive um, approximations. So Taylor polynomial, Taylor polynomials of sine x. All right, and well, somehow it's very long here. So now it's done, right? So this is uh, basically so, and this is the answer. So yeah, in the printed version of the slides, uh, the series for sine x in compact form is written somewhat a little bit differently. So they use 2n minus 1 here. So I wrote the sum from 0 to infinity minus 1 raised to the power n x raised to the power 2n plus 1 divided by 2n plus 1 factorial instead. Of course, it's either of them equals the series on the right. So it's up to you which of the two forms you want to use for calculations. Okay, now we're going to do the same to prove that e to the x can also be represented as a sum of its Maclaurin series. Basically, the idea is the same. So first, um, yeah, so notice that e to the x, um, if f is e to the x, then f prime is going to be e to the x, f double prime is going to be e to the x, and so on. So all derivatives of e to the x are just e to the x, and when we evaluate them at 0, we just get 1, right? So, and this is how we can find this Maclaurin series. But how do we prove that uh, the Taylor remainder goes to 0 if n goes to infinity, right? So what is the Taylor remainder? So if my f of x is e to the x, then f of x minus tn absolute value is going to be the absolute value of what? Of basically e, so the n plus first derivative, right? So let me write it. So derivative of order n plus 1 evaluated at some point c, but the derivatives of all consecutive orders of my e to the x function are just e to the x itself, right? So it's going to be just e to the c, e to the c times x to the n divided by n plus 1 times n plus 1 factorial. Well, and we can sort of take out e to the c, n plus 1 um, factorial times absolute value of x raised to the n plus 1. Now, c here actually depends on x, right? So c is not really a constant. So c here is not a constant. C in fact depends on x, right? So c is a number basically between 0 and x, right? So c is a number between 0 and x. If x is negative, then c is probably a negative number. If x is positive, then it's probably a positive number, but in any case, c is between 0 and x. Well, but if c is between 0 and x, then it means that c is going to be bigger than or equal than okay, so let me write it like this. So it means that in any case, c is going to be less than or equal than absolute value of x, right? Um, it could be smaller, right? So, but it is going to be definitely less than the absolute value of x. Cannot be more than that. So now let's look here. So this e to the c is really less than e to the x, right? So e to the c is going to be less than or equal than e to the um, absolute value of x. So which means that our Taylor's remainder f of x minus Tn of x absolute value, well, of course, it is bigger than or equal than 0, and it's going to be less than or equal than. Now I'm going to copy this, um, replacing e to the c with e to the absolute value of x, right? So this is going to be um, e to the absolute value of x times e to the absolute value of x. Ah, no, stop. Absolute value of x raised to the power n plus 1 divided by n plus 1 factorial. All right. And basically, because of the same logic as the sine x example, so here we have um, some some factor in front of it, so which is e to the absolute value of x. But now we need to take the limit as n goes to infinity, and if n goes to infinity, so e to the absolute value of x is just a constant, so it's not changing, right? But the rest of this is not really is changing, and it goes to 0, basically because of the same logic. So it's just absolute value of x raised to some power divided by factorial. So this goes to 0, right? And again, by the squeeze theorem, so our remainder, so the absolute value of our remainder is bigger than 0 but less than something that has limit 0. So whatever is in between also has limit 0. Okay, and basically here is the full solution once again. Um, and we conclude that the exponential function e to the x is equal to its own Maclaurin series, to the sum of its own Maclaurin series. So here are a few consecutive approximations, and that's all about the Taylor's remainder.